Hello and welcome to Lecture 45 of my class From Data to Decisions. Chris Mack, your professor for this course, and this is a lecture on subset regression, or how to find the best subset of a full model. First of all, suppose we are doing a multiple regression. We've got a fairly large number of possible regressor variables. Let's say more than 2, right? We have 3, 4, 5, maybe 10 possible regressive variables. Also, we have possibility of using some higher powers of a variable, x squared or x cubed maybe. Maybe some other functional forms are possible. And we can include interactions, so we can multiply 2 regressive variables together, for example. In any case, we've got a large number of terms that are possible. So many, in fact, that it becomes difficult to decide whether all of these terms are really necessary when building a model. So we will define the full model as the model that includes every single regressor interaction term, all the powers that we care to consider. So we just can't imagine or don't believe that any other regressor is possible or necessary. This will define our full model. Then a subset model will be any model with one or more terms missing. Our question is, which model is the best? Is the full model better than all the subset models? If not, is there a subset model which does better? Of course, defining what we mean by better is an important aspect of this, and we've already talked a little bit about that, and we'll talk some more about it. First of all, let's talk about testing individual terms. If I've got a full model with lots of different model terms in it, I might ask the question, for any individual model term, how do I know that that term should be included in the model? Well, one way of answering that question is to look at the coefficient and the confidence intervals about that coefficient. And ask, do those confidence intervals include 0? If they do, then there's a chance that true value of that coefficient, in fact, is 0. And the reason it's not 0 on my model is just because of random chance. Now, under the assumptions of least square regression, ordinary least square regression, we believe that the studentized versions of those parameters, that is the parameter value divided by the standard error of that parameter, that should be student t distributed. There should be n minus p degrees of freedom, where n is the number of data points, p is the number of parameters in the model. So we can do a hypothesis test. We can say null hypothesis, the true value of that coefficient is 0, and then we'll calculate a p-value based on that. So I should have put beta here instead of little b. I'll change that in the notes, but beta k equals 0. That is the true value of the hypothesis is 0. Calculate the p-value with a student t distribution, and then if it's greater than the significance level, alpha, that we've chosen, we can't reject the null hypothesis that, in fact, this coefficient really is 0, which means, generally, we don't need that term in the model. It's not contributing much information if its coefficient is 0. Now, things get a little more complicated than that in multiple regression. We're going to see this later. If I have more than one term that are not significant, statistically significant, that is more than one term where bk equals 0, null hypothesis cannot be rejected, that doesn't mean I can throw them both out because they might be correlated with each other. So that's a topic we'll talk about in the future. Another thing we can do to compare models is the partial f-test. This and what follows will all be based on comparing a full model to a subset model. Here I have 2 models. Model 1 is the subset of model 2. So model 2 is my full model. And I ask the question, are the extra variables that are in model 2 but not in model 1 actually useful? Are those added covariates informative? That's the the terminology we use in statistics. I've got these extra covariants, these extra terms that I've stuck in model 2 that aren't in model 1. Do they add information? Do they explain variance and why, or do they just randomly kind of fit the noise? Here's our hypothesis test. Null hypothesis is that all of these added predictor variables in model 2 that aren't in model 1 all have betas equal to 0. The alternative hypothesis is that at least one of those added predictor variables has a beta coefficient that's not equal to 0. To determine whether this hypothesis test allows us to reject the null hypothesis or not, we use the sum of square errors of the two different models. Remember, model 1 is a subset of model 2, so we'll calculate the sum of squares errors of the subset model, which will always be bigger than the sum of square errors of the full model. Look at the difference. This is called the extra sum of squares. So we look at the difference there and divide that by the difference in the number of parameters between the two. We compare that difference in the extra sum of squares to the mean square error of the full model. So this is the sum of square errors of the full model divided by the number of parameters in the full model. We can also express that same thing in terms of these adjusted R squared values. That resulting statistic will be F distributed with these numbers of degrees of freedom, and we can do a hypothesis test and compare it to, calculate a p-value, compare it to our significance level, and then decide whether or not the reduction in the sum of squares when we add those parameters is statistically significant. Here's an example of kind of a fun or novel way of using that a little bit differently than you might have thought. Consider this full model. I've got 3 regressors and 4 parameters. But I suspect that maybe something about the physics tells me that beta 1 equals beta 3. So physics, I say, theory, whatever it is, that says these two are really the same parameter. You just don't know it. So we want to test that. How can we test it? We can create a subset model that has a new predictor variable equal to the sum of x1 and x3. It's still a subset model because I don't have any new information that's being placed into this. In fact, there's less information because I'm only including the sum of these two variables, not the two variables themselves. Because they are both being multiplied by something I suspect are equal numbers, I can combine them with beta 1 as the coefficient of that term. Then I do a partial f-test on the subset model compared to the full model. That's equivalent to testing the null hypothesis that these two coefficients, beta 1 and beta 3, really are equal to each other. All right, here's another term we can use. This is very similar to some of the information criterion ideas that we've already talked about, but it's slightly different. The Mallows Cp is like an information criterion, but it is only geared towards comparing full model with a subset model. Remember, we had this measure of log likelihood, which was sum of square errors of my model divided by the true variance of the residuals. But I don't know what the true variance of the residuals are, so I have to estimate it in some way. Well, the way the Mallows Cp works, estimate the true variance using the full model. So we're going to test the full model compared to the subset model by looking at sum of square errors of my subset model with parameters p, and then I'll estimate the true variance as the mean square error of my full model. That means that this ratio is an estimate of chi-square, just like minus 2 times the log likelihood. But it's a special estimate that's based on comparing a subset model to a full model. The assumption here, we figure out what the assumption is. The assumption here is that the full model has no model error. That is, I've done a good job creating a full model that captures all the systematic variation, and mean square error of that model is then a good estimate of the true variance of the residuals. Now I'm going to do the same kind of thing. I'm going to add a penalty, just like the AIC. I'll add 2p. I'm going to subtract off n because I expect chi-square, if all my assumptions are correct, I expect chi-square to be about n minus p. So I subtract off an n, add 2p. Therefore, if everything is working well, that is, we've got a good subset model that also has no model error, then I would expect Cp to be about equal to p. And smaller is better. This is a good approximation only if I have a large number of data points compared to k, and I've got a pretty good full model. That is, my full model probably is capturing all the systematic variations. Here's an example of how we can use Cp. Because if we have a moderate k, that is a moderate number of terms in my full model, then I can calculate Mallows Cp for every single subset model. All right, suppose I have 11 parameters, like this example shows me. Right? Well, by definition, that number, Mallows Cp for 11, the full model, is going to be equal to 11. Sorry. It's going to be equal to p. But all these other models could be lots of different things depending on how good those models are when I reduce the number of parameters. So if I could calculate all of them, I could generate this chart of Cp versus p for all the different models. Now, I can do a couple of things with this. One is for any given number of p, let's say 7, here's all the possible models that have only 7 terms in the model. Well, one of them's best. This one down here has the lowest sum of square errors. Right? So that's going to be the best model. It's easy to compare models when they all have the same number of parameters. We could just use r squared, for example. And this one will have the smallest r squared. But how do I compare when I have different numbers of parameters? Well, for any given number of parameters, there's a best model, and I can kind of look at how all of those best models connect up. And only some of them are below the line Cp equal to p. Right? Cp equal to p is about what we'd expect if we had the right model. So all the models that are below that line are potential candidates, probably good enough models. Remember, sometimes the statistical difference between these models could be slight, and the deviation in Cp are just due to randomness. But all of these below Cp are candidate models for us. And all these really high Cp ones are models we're not going to consider anymore. This is our third test for a subset model, or sometimes called a nested model, is the likelihood ratio. Well, we can create a likelihood by calculating linear regression for the full k parameter model, and then we can calculate the likelihood for the p subset model. Well, the likelihood for the full model is going to be greater than the subset model every time. But we can calculate this parameter g squared as the likelihood ratio minus 2 times the log of that ratio. It's essentially the difference between the two information criteria, ignoring the difference in the number of parameters. So it's only comparing likelihoods. For a large value of n, large number of data points in the sample, we can say that if the subset model still doesn't have any model error, then g squared is approximately chi-squared distributed with k minus p degrees of freedom. Therefore, we can test g squared against a chi-squared distribution, and if g squared is too large, we can reject the subset model as being having fact equation error. It's missing terms that need to be there. But if we can't reject it, well, then we might as well use the simpler subset model rather than the full model. Well, one thing I mentioned is if the number of parameters in the full model is reasonable. I showed 11, here I show 9. If it's in this range, it's possible to just let your software crank through all possible subset models. If you can do that, then it becomes kind of a little bit easier to evaluate which of these models might be best. So again, for any number of parameters, calculate the best model pretty easily, just using any of these metrics. Here I use R squared, here I use adjusted R squared, here's Mallows Cp, here's the AIC, here's the BIC, also called the SBC. This one is a metric I haven't talked about, not going to talk about. It's another one called PRESS. And this one is not showing the likelihood ratio, but of course you could have included that as well. And there are some others that other people use that have similar ideas and feelings behind them. Right? For any given value of P, there's a best model. And so these dark lines are connecting every best model together. And with 9, the full model, that's the value of these parameters for the full model. Well, things like R squared always gets better, but you see it does kind of plateau out. Adjusted R squared can go down, but the AIC and the SBC also go up as I get too many parameters. We find that P of 5 gives us a minimum for both the SBC and the AIC, and so we have a specific model out of all of them that produces the optimum AIC. It's going up kind of slowly, so maybe it's only a little bit better than some of these other models. But since parsimony is valuable in most cases, we might pick the P equal 5 model. We could decide to give up on some quality of fit, get a simpler model, and maybe the P equal 4 best model is going to be good enough for our purposes. This is the kind of decision that requires problem domain expertise. It's not a question of statistics. It's a question of scientific judgment. All right, let's talk about what we've learned when it comes to subset models. You should be able to quickly and easily explain the use of the partial F-test for a subset. How is Mallows Cp used to evaluate subset models? And finally, how is the likelihood ratio used to evaluate subset models? That's the lecture for today. This lecture will use R to actually perform some of these subset model comparisons. Till then.